Okay, so when I was preparing the slides for this badly named talk, I thought it would be a cool idea to start with the definitions of AI and machine learning and neural nets and stuff like that. So I asked my colleagues who are here, hey, help me find a good definition of what would pass as AI. And an hour passed, and things were said, feelings were hurt, and we reached no conclusion. So in the spirit of this tweet, let's drop PowerPoint for a minute, and let me show you something cool. So just to give you a little bit of context, who here loves doing their expense reports? So one of the most tedious and repetitive and boring tasks that everyone does is read stuff on paper and type it into whatever system. Now, you do this every day. And what some companies tried is, well, let's say you've been to your favorite restaurants for the nth time, and you upload your receipt. And fortunately, because the system already seen exactly this receipt, but with different totals and stuff like that, they memorized how the receipt looked like, and now they're gonna go to and extract all data from the exact same spot. But if you go to a new restaurant, then you're pretty much on your own. And they have you highlight. I think I should have had a clicker. I need a pointer. OK, so imagine I have a pointer. You'd have to, oh, there it is. So then you have to go into that software and basically highlight, well, can you see the pointer? Never mind. So you'd have to highlight, like, where are the totals and what's the vendor name, what's the address. What? Good idea. OK. So you'd have to highlight, like, here's the vendor name, and here's the address, and here are some numbers that I want to extract, and here's the total. OK, what we did at UiPath is we tried to build a model that would, when you show it a new receipt that you've never seen before, like, I mean, the system never seen it before, OK, it would just know that it's a receipt, just like a human would, and read all the relevant information. You see, we have the vendor name, we have the address, we have the date, we have the total here, line items, so pretty much everything. And it's not immediately obvious why it works, but what I'm going to do now is break the problem down and walk you through some of the projects that led us to this solution. So I'm going to switch back to PowerPoint. One of the most common tasks in computer vision is called object detection. And basically, you have an image, and what you're interested in is what objects are in the image and where they are. This is an image from the COCO dataset, and you can see we have the coordinates and types for a bunch of cars and a traffic light. Now, this dataset is huge. It has hundreds of thousands of images and dozens of classes, from cars and trucks and motorcycles to cats and dogs and bananas and a bunch of other stuff. And this makes it a very useful data set for researchers. And why is this the case? Well, because researchers are interested in building novel approaches that work well on a wide range of scenarios. And this being a very hard task, you have to come up with something really good so you can perform at least decently on it. And here are some numbers from some of the more modern models that TensorFlow has available. On the last column, you can see the score, which goes from 0 to 100, 100 being perfect. MAP stands for mean average precision. It's a little more complicated formula, but basically what it means is you get penalized for missing an object. So I have a mouse now, yeah. So for example, if you were interested in finding the traffic sign and you missed it, you would get penalized. But also, if you hallucinated the car up in the sky, or even here, but it's not there, you also get penalized. Now, these numbers in the low 40s are an order of magnitude bigger than anything that has come before neural nets. So we know that they're very powerful. On the other hand, these numbers are so low that they are not usable in any real-life application. Like, just imagine if your self-driving car would fail to see 1 in 20 pedestrians. You can't really afford that, right? So researchers don't mind this, and they are more interested in gaining insights. And if they gain even small improvements, that gives valuable insights. But if they fail, they are interested in why did they fail, and usually this also gives useful insights. Engineers don't have this luxury. We have to ship, it has to be reliable, it has to pass QA, and nobody has to die. So we are interested in maxing out those numbers. So what we do is, when we have a new project, we'll try to frame it in terms of what's available from academia, and then we are gonna reduce the problem and just ignore all the cases that we're not interested in. By making the problem narrower, it's easier to gain better performance. So, for example, if you're building an OCR engine, and if you're Google or whoever who's building an OCR that you want to use in every scenario possible, you're interested in reading text from everywhere. But if you're interested in scan documents, for example, you can just focus on that, and the model will be easier to train. And of course, you're going to get great performance, but at the expense of it not being usable in any other scenario. Now, I had to use the logo for the presentation. And so, a project that's very dear to my heart. The first project that we tackled, it's UiPath using machine learning, is image-based automation. You've heard Remus before, showing you the secret sauce with the driver and how we interact with different kinds of applications. What we try to do is just what we try to do with this project, which is an alternative approach, is just rely on the screenshot and interact with the application exactly like a human would. So basically, we are interested in detecting UI elements, like anything that you would want to click or type into, and we are interested in finding the text, so you can extract it or do whatever decisions you need based on it. So I'm going to pop up a demo. OK. So I'm just going to keep the 7-zip on my screen because it's less cluttered. So I'm moving my mouse around, and here you can see what the model is detecting in real time. It's very similar to what you've seen before from Coco, because it's exactly the same problem. We just narrowed the kind of data that we're looking for. We narrowed it down to just UI elements in applications. And I'm going to move around in a couple of menus so we can play around a bit. So we see buttons, we see checkboxes, radio buttons. And this basically allows us to automate just having a screenshot. Now, of course, we also need, I can stop the demo so I don't lose my battery. OK. Now, once we know how to detect objects, be them UI elements or whatever, we can build upon this task and say, OK, we want to read text. And I need to start up another demo. Give me one moment. So this is just a simple front end to our OCR engine. I uploaded an image. It's easier this way. And you can see we still have these bounding boxes. But now, instead of just knowing whether they're buttons or checkboxes, we can actually read the text that's inside them. How we do this is we use the same model as before. And after we get the boxes, we cut them out. And we use another model that just passes through it and extracts the characters. you can see it missed, like these numbers here and the C. So it wouldn't have 100% MAP, but we are still in the high 90s. So it's very usable. Once we know how to extract text, we can go even further and do information extraction. Now we can use a separate OCR that's good on photos of documents. And after we have all the boxes with all the text, we can put them in context with another model and understand not only that there's a rectangle there in which there's the text center core. We know that center core means it's the address on this receipt. And there are not, you can see this is quite a hard receipt, like it has shadows, and it says nowhere that that's an address or it's a vendor name. Okay, what are the next steps for us? Well, for these projects, now the models are pretty big. Like they require a GPU server if you care at all about throughput. So we are interested in building smaller models that can learn from the larger ones and hopefully deploy them using only CPU servers, or maybe even deploy them on edge. And for UI understanding, we want to tackle more complex UI elements, for example, detecting whole tables or windows, not just individual controls. For information extraction, which will soon be in general availability. By the way, with the first one, you can actually download it and use it from Studio. It's quite awesome. Now, for information extraction, of course, for now, we support only a few types of documents and just English and Romanian, because we have a lot of receipts in Romanian. But hopefully, we're going to expand that to multiple languages and multiple document types. We do have some other projects, but I don't think we're going to have enough time to talk about them. The takeaways here would be industry and academia focus on different things. Academia wants small improvements that have a lot of insights. We focus on shipping code. And because academia has this very broad approach, this creates a lot of opportunities and low-hanging fruits, because you can take those generalistic approaches and narrow them down on a specific problem, and there are a lot of chances to find something that you are the first one to try to tackle it this way. And of course, you should always leverage research whenever possible, so you should really understand your problem, read the literature, and only after you have a strong baseline using what's available from open source, like TensorFlow has a great repository called TensorFlow Models. Facebook AI Research also has the Detectron. And only after you have a strong baseline, you should start tweaking around with a model and more fancy stuff. And I was prepared for a failed demo. That's all. And we have 4 minutes for Q&A. Thank you. There's a very bright light, so...
Salut, aici.
Okay. Hi.
Cum ați antrenat modelul pentru... I should speak in English, right?
Yeah, we have some...
Okay, sorry. How have you trained the model for recognizing the UI elements in the screenshot? I mean, where did you get the label data? Who labeled that images?
Yeah. Yeah, we have people that spend a lot of time tagging them. We started by... It's like a baptism by fire. So each of us actually started manually annotating images. We tried the approach of generating UIs, for which we already know where the controls are. Well, it turns out you can't really imagine a general enough image generation process, and the neural net will just learn exactly what you did. And it learns perfectly that data, and it performs horribly on anything else. So we invested in people who just spend dozens of hours labeling them and collecting data, and we also had to invest in our custom tagging applications.
Hello, my question is about the program. So if you can tell us something about the size of the code and the programming language.
Size of the code, what do you mean?
How many classes, how kilos or something, if you have some estimation to understand the complexity.
Okay, so for object detection, you can start out writing virtually no code. Because, as I said, you have awesome open source packages that are awesome baselines to begin with. And the TensorFlow models repository is huge. You can spend weeks just browsing through the code and trying to understand it. But in terms of what we've written, well, we forked that project and made little tweaks. Maybe we have, I don't think we have more than 10 or 20 files that we had to change in our fork of TensorFlow models. And what we have is lots of code that manipulates data, like generating augmentations and moving stuff around. But in terms of writing neural nets code, not so much for the object detection project. Like for UI understanding, that's the case. For the other projects, we had to write a bunch more code. The code complexity is not comparable to a large-scale software project. Here, it's very little code, very subtle code. Like you have 5 lines and you spend 2 weeks to understand them.
And it's Python?
Yeah, sorry, yeah, Python. Python for building the models, but then when we ship them, it's not necessarily the case. Yeah, so low-hanging fruits, what I meant is, for example, we need an OCR engine, right? Well, nobody's built an OCR engine that's awesome at UI automation or awesome just at scan documents, right? So that's the low-hanging fruits for us. You don't have to invest 20 years in building an OCR engine that's a jack of all trades. The low-hanging fruit is just attacking this niche. As for other low-hanging fruits, I don't know why I'm not an entrepreneur, sorry.
Sorry.
Sorry, he has the mic.
Here. Regarding generating the models, the UI stuff, why aren't you trying a generate adversary model for doing this? A GAN, it's one.
Okay, so because if we use a GAN, we'd learn.
It has a randomness there, so.
Yeah, it has a randomness, but it will just so have you looked at like faces generated by GAN? It has those monsters or.
It's a paper that I think came out a day or two.
Yeah, so
it's called Big GAN, and it's pretty much.
Big GANs are old stuff. Okay, so you have supervised learning and unsupervised learning. Unsupervised, which is GANs, is very interesting. And at least from what I know, and when I've seen the actual numbers, it works awesome. It's awesome that it works at all, but the performance you gain by using like the encoder parts and then a classifier from a GAN is maybe 10 points lower from what you'd expect with like the pre-trained TensorFlow models on Coco. So if you try a GAN on the Coco dataset, I guess you won't even get to 30 MAP. So because we're trying to get as close to perfect as possible, labeled data is the only way to go. It's an interesting approach, but it will just be kicked back by QA in our case. Thank you. We can all go to the toilet now.
Good work, man.
Thanks.
Great to hear you.